Okay, you are muted.
Thank you. We're presenting an image that's worth 16 by 16 words, transformers for image recognition at scale. Our presentation is going to follow the general outline of the paper, the introduction, just a general introduction, the objectives of the paper, some background related work, the methods they use, the authors use, the experiments they ran, because they ran a lot of them in order to test their models, and then pros and cons of what they've done. So as we learned in class, natural language processing was already using transformers. It involves pre-training on a large data set and then fine-tuning to a more task-specific, smaller data set. Some other computer vision papers have used transformers. However, they were very customizable and very complex. And this paper wanted to use transformers in a more general, scalable manner. To do this, they just apply a pure transformer onto image patches. It's similar to NLP, but instead of using words as tokens, they use image patches as tokens. As I said, for images, this requires a lot of data for pre-training, 14 million up to 300 million images. And as we'll see in the study, the more images, the better. So the objectives of the paper, they wanted to apply the transformers to computer vision problems. And they did this with something called a vision transformer, or VIT for short. They wanted to do this without relying on CNNs, so they did build a hybrid one that used CNN and transformers. To show the robustness of it and to test it with different parameters, they wanted to use a variety of models and test it on different data sets, both for pre-training and for fine-tuning. A great goal, of course, would be to have better results than CNNs do, which they achieved, and ideally also to lower the computational complexity.
So in related work, sequence models have been around for a while in computer vision tasks. In relation to deep neural network models, there have both been recurrent neural networks and short-term memory networks like LSTMs. A couple of problems with them. They were slow to train because they had a lot of sequential processing, and they also typically had a limited memory, so they operated on a small window size. Transformers, as we know, started to arise in natural language processing tasks in the paper Attention is All You Need, introduced in 2017.
So where should I look when I'm talking about your big screen, right? Where should I look when you talk?
Can you see my cursor?
Yeah. Okay, and how about the figures you are showing?
Okay.
So should I look at those also, or just your bullets?
Just the bullets for now. So transformers allow for parallel training of longer sequences, and some models from the literature that kind of inspired this that we'll talk about and see direct inspiration from were BERT and GPT. On the top here, you can see an example of what a recurrent neural network could do, processing one-to-many or many-to-one or many-to-many inputs to outputs. So that's one related network used in computer vision today. Below is just an example of the transformer architecture where we could take multiple inputs in the input embedding here and process multiple outputs. And then if we look to compare this paper VIT to current state-of-the-art on ImageNet, we know from history that convolutional neural networks have really dominated classification tasks. Transformers have recently started to overtake them with some caveats, which I'll go into in a second here. So if we look at this table here, you can focus on the first model. This is the transformer, the vision transformer, huge with a 14 by 14 input patch size. It achieved 88.55% accuracy on ImageNet in the top one accuracy. In comparison, we have one of the latest strictly CNN architectures published in the same year, and also by the same team at Google Brain, running this efficient net model, getting 90.2% accuracy. There was an improvement to this VIT paper published in the same year, which bumped their accuracy up to 90.45 with a similar model. And then also looking at a hybrid architecture that uses both a convolutional network in the front half and a transformer in the back half. Currently has the highest reported score for classification on ImageNet, which is at 90.88. Sorry, and just a caveat to note is that all of these papers were produced by the Google Brain team, which is their AI research division. It was all trained with data that is not available to the public. So these scores may not be representative of what we could train. It's kind of preloaded on extremely large data sets, which we'll touch on.
Can you see my cursor or hello? Can you guys hear me or?
Yeah, we can see
Okay,
the cursor.
okay.
And,
All right,
yeah.
so this is the talking about the model that they use to create a vision transformer. This is the picture provided within the document. This is a very good diagram and and it kind of shows the way that the network or the model is able to go through the data. As you can see that it's based very heavily on the original NLP transformer, and they even mentioned this in the paper. As you can see in the transformer encoder on the side, there's the skip nets, normalization layers, and MLPs that you'd find in the original version of it. So the first thing we're going to talk about is this section right here. This section involves splitting up the image into subsections of patches. That's where the title of the paper comes from. 16 by 16, an image worth 16 by 16 comes from the actual size of the patches. So as you can see in this picture, the reason that you need to do this is because transformers are very, very, very computationally intensive, right? So if you were to have an image that was 255 by 255, right, that would be, and you were trying to pass each individual pixel in as input, what would end up happening is you would have 255 squared computations, which would be just astronomical. So Google's solution to this was to split the image into individual patches. Now, their numbering system specifically is that they used a one-dimensional numbering system as opposed to a two-dimensional numbering system, mostly because they didn't find much difference between the two. So opposed to 1, 1, 1, 2, 1, 3, 2, 1, etc., they just do 1, 2, 3, 4, 5, 6, 7, 8, 9 through the patches. And another thing with the patches is they are square patches with the same length and width, and they have to fit into the image evenly. So next slide is the next part we're going to look at is the two embeddings that they use to pass into the transformers. So this picture explains it pretty well. The transformer passes in two kinds of embeddings. The first embedding is what's called the patch embedding. And the way that this works is that it will take an individual patch and it will flatten it out into well, it'll flatten out every single patch into a matrix of size n p squared times c. So n being the number of patches and p squared times c being the actual size of an individual patch. And what it'll do is that it will multiply these patches, these flattened out patches, with an embedding matrix, which is actually a learned matrix, right? So what's happening here is very similar to what would happen in a linear layer of the neural network, for example. And so you're going to take these patches and multiply them and get some kind of resulting embedding matrix of size D, which can be seen down here, right? So D is the size of the embedding matrix. You can change that to whatever you want it to be. And so the other thing that it passes into as well is a positional embedding, because transformers are positional invariant. So if you were to pass these patches in a different order, you would still get a similar answer. So you need to pass these positional embeddings along with the patches so that the network can understand positioning. So in NLP applications, they use a trigonometric means of doing it, but here they use a learned model where they do a row lookup matrix, and essentially each patch has its own embedding matrix, but it isn't implicitly coded. So the model itself is learning this, and that's mostly to lower the inductive bias of the network. So here's just some examples of, and also the other thing to mention is that each of one of these patches flattened out is having the same learned E matrix applied to it. And the other thing to mention too is that at the end, both of these are concatenated together or added together in a lot of applications that I've seen. So this EPOS is this right here, and it's added to the entire embedding matrix. So the next thing to mention is the CLS token, or the class token, and this is something that they inherited or that they took from the BERT architecture. And essentially what this is that it's pre-appended to the beginning of all of these embeddings that are going to be passed into the transformer. And essentially it is what's going to be used to classify the image in the MLP head, which so at the very end, the last hidden layer of the CLS token is used to classify whatever image it's been given. And so this CLS token is interacting with all the different patches, and it is also learned as well. So, and it has a positional embedding so that the network can also learn that this kind of holds a special 0th position. So another thing they found out is that instead of using a linear projection in order to get the patch embedding, what they decided to do instead was to almost combine both the steps together and use a 2D convolution. And they have similar results, but the main advantage that this gives is that it's more efficient because a lot of GPUs are made in a way that optimizes convolutions. So in a network that is supposed to go away from convolutions, they found that they can also use convolutions to do it. So yeah.
Seeing my cursor. Controls. Okay. Okay, I'll be explaining here the fine tuning, how they have used the fine tuning. Are you able to see my cursor?
Yeah.
Yes.
Okay. So typically they pre-train the network, the model with the large data sets, which is data set A here. The model will be trained with the large data set, and this step we call it as a pre-train. The pre-trained data set, the pre-trained model will be fine-tuned with the smaller data sets. So this step we call it as a fine-tuning. So the reason why they pre-trained to take the advantage of the next we don't have to train for each and every problem by giving the training with the large data sets. So this is the advantage of the pre-training. So during the fine-tuning, they have approached two main steps, which are one is removing the MLP head here. So this is the pre-trained positional embeddings it will have. By removing this, after removing this, they have added with a feed-forward layer, which has the 0 initialized dimension with the with the downstream classes, which we want to classify the images. So the number of classes which will have our target data set, less classes. That is the reason we will remove the prediction, and whatever the target data set we want to use, that is a data set B here. We will fine tune with the data set B. So
you guys have 10 minutes left now, so you need to finish it in 10 minutes. Okay.
The second important, okay. The second important step in the fine tuning is the higher resolution. It is they have benefited by feeding the images with the higher resolution. During the higher resolution, it's the pre-trained positional embeddings will lose their meaning. To overcome that, they have performed with the 2D interpolation of the pre-trained positional embeddings. And these are the two main approaches they have taken. Yeah, that's all. You can take the control for the next slide.
Okay, for the data sets, there's nothing really too important here, just two main points I want to make. For pre-training, just take note at how many images are involved in the pre-training data sets. And they do experimentation with all these data sets. For fine-tuning, they also use a variety of data sets, but they have much fewer images in it. So that's one thing. Also, take note that it's not like they just did one experiment and said, okay, these are our results, with ImageNet, they're really good. They tried all different architectures, configurations, all changing parameters to make sure that their design was robust. For pre-processing, the pre-trained images are cropped. They have horizontal mirroring, and they resize them to 224 by 224. But as was mentioned earlier, for fine tuning, they find that you get better results with a larger dimension. So they have it at 384 by 384. For the VIT models, they have base, large, and huge. Base and large can use 32 by 32 patches and 16 by 16 patches. And then huge uses 14 by 14. Over here are just some general parameters like the number of layers, the MLP size, the number of heads. Hidden size D, this is the latent matrix size or length, which is what is actually fed into the transformer. They use a variety of CNNs to test on, ResNets of different layer sizes, 50 through 200, but they use group normalization instead of batch normalization, which allows them to take into account any kind of cross dependencies between the channels. For the hybrid models, they simply use a ResNet 50. At stage 4 of the ResNet 50, they take the feature maps that are output and they feed it into the VIT with patch size being 1 pixel. Finally, real quick, in training, they found, unlike SGD, they found after some experimentation, as you can see in this table down here, on average, Atom Optimizer performed better with ResNet than SGD. So that was their design choice with their various hyperparameters there. And then for fine tuning, they did use SGD with momentum, batch size 512, no weight decay, and cosine learning rate decay. They use two metrics to report their results: fine tuning accuracy, which is after doing pre-training and fine tuning. This is the most important result here. This is the big one. But for some of the stuff to justify their design choices or their parameter choices, they would use few shot accuracy, which allowed them to use a smaller subset of data. And this would process a lot faster so they could quickly see in what direction their choices were going.
So who is talking now? Because we can't hear.
Yeah, you're muted.
Kishore, I think you're muted.
Okay. So I need to take the control. Yeah. These are the data sets which we have, which they have used for the pre-training. One is ImageNet small data sets. The other one is ImageNet large data set and the JFT data set. It has ImageNet smaller one has 1.3 million images, and the large one is 14 million, and the JFT 300 million. And the classes 1,000 classes in a small data set, and 21,000 and 18,000 in the JFT data set. The JFT data set, which they have used Google's private data set, which is not available in the public. So the next one, these are the scaling study they have observed during the transformer network. When they have first they have trained with the ImageNet small ImageNet small data set, and they have used different models, which is the vision transformer high 14 patch size, and the other one is 16, and the ResNet. These are the metrics they have, the accuracy metrics and the computational, which they have used TPU v3 core days as the metrics. So when they have used in the smaller ImageNet set data set, they the vision transformer is did the worst performance compared to ResNet performance. The ResNet did very well with the small data set. When they have used with the ImageNet large data set, the vision transformer is comparable with the ResNet. Both are it looks same. But when they have used with a JFT bigger data set, which has 300 million images and 18,000 classes, the vision transformer is better than the ResNet, which they observed for 1% better performance compared to ResNet. Finally, based on our experiments, we have observed the vision transformer is performing well when you have increasing the data set. The maximum data set they have used for 300 million data set, but if we want more better results, this is the observation, better results, you have to use the more than 300 million images. That is where we can see more better performance with the vision transformer. That is the observation. Yeah, that's all.
There we go. Sorry. So the next 4 slides will just kind of tell us how the network is representing data. So if we want to look at an input image here and understand where the network is queuing on, we can build a map of where the attention is activating. So if you look at the example on the left, we can relate any input to output, maybe the class label for dog or plane in this case, and relate that to all of our inputs by simply computing a forward pass and then averaging the activations from each attention head. Once we do that, you could kind of recursively multiply those activations together and then sum them up to get basically the relationship between the activation in the attention head and the input space. Another way of, I'm going to skip this one for time, but this is just how we compute the embedding. If we want to visualize kind of what the embedding is learning in the model, we can first take the E matrix, which is applied to each of the image patches, and visualize, what do the principal components of that embedding matrix look like? So E is a matrix. If we apply PCA to it, we get a list of features, of new descriptors and we can kind of visualize, you know, what is important and learned in that embedding E. So if we look at the first couple of examples here, we can see that the principal components of E are showing very similar activations to something that we would see in like the first layer of a convolutional neural network here. It's just an intuition. The principal components do not, you know, necessarily relate to the model's performance. This is just kind of a way to visualize that the embedding is kind of learning things that we would expect to find, you know, similar to what we see in image-based or in convolutional-based methods for understanding image data. And then what does the position embedding learn? So we have that other matrix, E position, and we can look at all patches N and compute the similarity between the rows of E with themselves and all of the other rows. So we can compute the similarity between any given row E, which reveals, you know, the actual position of the input patch. We can start to build a map of how similar each of those positions are with each other. So we can kind of intuitively think if we laid this out, we would have maybe 7 by 7 input patches, which would correspond to a long sequence of patches. If we looked at the first patch, which was represented in the top left corner, we could see that there's a very high similarity with the same row because that's exactly the same row that it was computed on. But if we look at the similarity between that row and others that are in the same row within the overall image, so that would be these patches in a corresponding image, you can see that they're still activating, there's a high similarity between that and where it actually is. And that occurs in both the X and Y direction. So we can kind of understand that through this similarity metric, position is kind of intrinsically learned within that position embedding matrix here. And I'll address that question afterwards. So another kind of interesting thing to note is that, you know, in these models, because of the way that we're laying out all of the data and feeding it directly into the network, we can get attention to across many pixels very early in the network. If we look on the left, you can see kind of what a receptive field would look like with just a simple 3x3 kernels in a convolutional neural network model. So as we stack layers in a traditional CNN, you know, we take local features and keep building more layers on top of them to get access to more pixels as we build the network. In the vision transformer, we can already see in the earlier layers that this attention is already spread up to like 120 pixels away. So that's one of the benefits of the vision transformer is that we don't need super deep networks to have an understanding of globally important features. Earlier layers in the model are already learning that to attend to features that are very far away.
They also performed some, they also performed some experimentation relating to self-supervision, which is important in transformer architectures because they require so much data and labeling is so expensive and time consuming that if you can take existing labeled photos and somehow manipulate them and pre-train the model on a different version of the image with, in this case, missing information, then it can actually help you train things a lot faster and maybe even better. So in the case of this in the case of this paper in the vision transformer, the way that they do it is that they use something very similar to the way that they do it in BERT, where in BERT they substitute words for mask tokens 50% of the time, 15% of the time. In this case, it's 50% of the time, where 50% of the patches are replaced with mask tokens. Well, 50% of the patches are chosen to be changed, and 80% of the time they're changed to mask tokens. 10% of the time they're changed to another patch in the image, and then the rest of the time they're not changed at all. So this happens during pre-training, and they messed around with this and they just changed the BERT implementation to one that would work for image patches. So okay, I can't change. Oh, here we go. James, I gave control back to you, so you can just.
So the advantages, obviously, the self-attention is kind of a breakthrough. It's very useful. A big advantage over CNNs is that you can parallelize the training, and also you can learn the spatial mapping of where the patches were pulled using the positional embeddings. You can spread your attention across the pixels, even as we were just seeing, even on early layers. So you have early on, you have a global understanding, and the diagrams in the paper were clear and well made. The biggest disadvantage is this is trained on private data that's internal to Google, and your average person or researcher may not have access to such a huge data set. So that could be a problem for pre-training. And also for extremely large networks, they are not suited for deployment on edge computing. And
I would also like to note that one of the big disadvantages is that since it works on only large data sets, it works well on larger data sets that are astronomically large. It can be very hard for even like the small business or something to take advantage of maybe the power of transformers. So, yeah.
All right, that concludes our presentation.
Okay, good.